in general, the solution to the force vibration case is a function of the type of excitation. F of t, in general, could be any time-dependent function. To start with, we'll assume that the excitation is a harmonic excitation of the form f of t equals f cosine omega t, where capital F is the amplitude of the excitation in newtons, and omega is the frequency of the excitation in radians per second. So if we substitute the assumed form of f of t into our equation of motion, we get an expression which is equal to mx double dot plus kx equals capital F cosine omega t. Now, from our previous analysis of the free vibration system, we know that the natural frequency squared is equal to the ratio of the stiffness k over the mass m. And so we're going to find that we can rewrite the equation of motion by dividing through the mass and write it as x double dot plus omega n squared x is, as in the case of the undamped oscillator undergoing free vibration, we'll solve the equation of motion by assuming a solution. In this case, we'll assume a particular solution of the form xp of t is equal to an amplitude capital X times cosine omega t, where omega is equal to the excitation frequency of the applied force. Now, in this assumed solution, the only undetermined parameter is capital X. And so what we'll do is take this solution, substitute it into our differential equation, and solve for capital X. So if we take the necessary derivatives of our assumed solution and substitute the particular solution into the equation of motion, we get the first expression that you see on this chart. Now, this expression can be rearranged into the expression on the bottom, where we have a term omega n squared minus omega squared times the undetermined parameter capital X times cosine omega t, and that has to be equal to f over m times cosine omega t. Now, once again, the solution has to be valid for all times, and so we note that the cosine omega t is common on both sides of the expression. Therefore, the undetermined parameter can be solved by looking at the coefficients in front of the harmonic function. So for this equation to be valid at all times, we can solve for x, and we get the solution x equals f over m over the difference between the natural frequency squared and the excitation frequency squared. So again, we can rewrite this. We can take our solution for capital X, substitute it back into the particular solution, and now we know that the particular solution xp of t is equal to f over m over omega n squared minus omega squared times the harmonic function cosine omega t. Now that we know the expression for the particular solution, the total solution is the summation of the homogeneous solution xh of t and the particular solution xp of t. So as we discussed earlier, the homogeneous solution is given from the free vibration case, and so the total solution is given on this chart. Now, you note in this solution a couple things. One is this solution is only valid when the forcing function is equal to the assumed forcing function f cosine omega t. For other types of forcing functions, we would get different particular solutions. Also, we note that there's still two undetermined parameters in this expression, the amplitude A of the homogeneous solution and the phase angle phi also of the homogeneous solution. Now, in the case of the free vibration, we solved for these two undetermined coefficients by using the initial displacement and the initial velocity. That is exactly what you would do in this case. In this case, we would take the total solution x of t, solve for the velocity x dot of t, set those equations at t equals 0 equal to the initial displacement and the initial velocity and solve for a and phi. Now, there's an important note. If you look back in the free vibration case, we got solutions for a and phi for the case when f of t was equal to 0. It's important to note that those solutions that we obtained for the free vibration case are not the same as the solutions you'd obtain in the forced vibration case. So if you were looking for the total solution given the forcing function and given the initial displacement and the initial velocity, then you would use the total solution on the previous chart to calculate a and phi, and those would be different in general from the case of the free vibration.